So this is where we left last time, and we were going to start to discuss dynamic branch prediction as a solution to decrease the likelihood of having to stall during the execution of a branch instruction. Now, this is obviously, as I explained last time, a larger problem in deeper pipelines where you have pipeline stages in the order of 9, 11, 13 pipeline stages. And if you have to flush the pipeline and introduce stall cycles, the number of cycles and the penalty for that is much larger. Also, where you have a superscalar organization, which we will see later on what that is exactly, but that essentially is where you replicate pipelines and they may not be for the same functionality, but you have pipelines working in parallel to execute the stream of instructions. Now you have multiple pipelines, obviously multiple stages per pipeline. So you may have a large number of instructions being executed in the processor at any given time. And if you have to rewind your execution stream and flush the pipeline or the pipelines, that may cause a lot of it may be a big impact on performance. So one way to try to mitigate that is to use dynamic branch prediction. And there are several aspects to that. So one aspect of that is a branch prediction buffer, which is really a history table of what has happened to the prediction that you have done before. And also you can have a branch target buffer. So instead of computing the branch target addresses every time, you have stored the recently used branch target addresses, so you don't have to compute them. You have them readily available to use them in your branch prediction scheme. So in dynamic branch prediction, the essential steps are the following. You check the table and you can expect the same outcome that you have had recently. And you start fetching from the that target, which is either the fall through, which is the instruction immediately following the branch instruction, or the target that has to do with that prediction. Of course, if you are wrong, you do have to flush the pipeline, reverse your prediction, and start fetching from the other target. But what we want to do is minimize the number of times that we are wrong. Eventually, we are going to be wrong in any prediction scheme, but the question is, how do we minimize that and minimize the penalty for being wrong? The simplest type of predictor is what we call a one-bit predictor. So we're going to just predict the outcome that was successful last. Now, this has a shortcoming in the sense that when you have nested loops, you're going to be wrong twice in a row. You're always going to be wrong twice in a row. And a lot of software have, a nested loop. So that's a common construct. So that is a big drawback to the one-bit predictor. So we can see here a simulation of a one-bit predictor. So let's say that we start arbitrarily with the assumption that the branch is going to be taken. And since we're talking about loops, we're going to be branching back. So we predict that it's going to be taken, and we are correct. And we're going to follow that trend and going to be correct for as many times as the loop is in effect. But when we are going to exit the loop, we're going to be incorrect. And then we are going to predict the reverse. We're going to predict that the branch is not taken because we were wrong last time. So we reverse our prediction. and then we are incorrect again because we are exiting the second loop and we're not branching back, or we're branching actually back in the outer loop, rather. So we have that situation for nested loops with a 1-bit predictor. So in this simple simulation, the accuracy is 80%. Nothing magical about that number. That's just a function of the length of this simulation. And we can have another type of simulation where we actually, the loops are shorter in the sense, in the way that they are arranged. So in that sense, with a 1-bit predictor, if we start with assuming that the branch was taken, we assume that, and our prediction is correct, then the branch is not taken, and we're incorrect. Then we assume that it's not taken, but it is taken, so we're incorrect again. Now we flip our prediction, but we are incorrect again, and you can see how our performance can really suffer as a function of the existence of nested loops and the fact that we are flipping our prediction every time that we are wrong, but we are not taking into account for the nesting of the loops. So one way to solve that is to use a 2-bit predictor, which instead of having 2 states, as implied by the 1-bit predictor approach, we have 4 states, which is what we can afford with 2 bits. And here we're able to remember 2 consecutive outcomes. So if we start predicting that the branch is taken, as long as our prediction is correct, we stay in that state. If the branch is not taken and we are wrong, we move to another state, but we still predict that the branch is taken. We don't change our prediction, but by switching states, we remember that we were wrong once. If the branch is taken, we were right, and we go back to the original state, so essentially resetting our trend. But if we are wrong again, we go to a third state, and at that point we have remembered through the state machine that we were wrong twice. And only when we are wrong twice is that we switch our prediction. If when we are predicting that the branch is not taken, we are wrong, we go back to the previous state. So that way we're absorbing the fact that we are flipping the outcome of the branch outcomes. If the branch is not taken, so we were right, we predict that it's not taken, but now we have remembered that we were right twice, and we stay there as long as our prediction is correct. If we start being wrong in this state, we basically reverse the state path, just like we did before, and we start remembering that we were wrong once. And if we are here and we are wrong, we go to this state and we have remembered that we were wrong twice and switch our prediction. If we are right here, we go back to this state, essentially absorbing the fact that we were wrong once. So this is the 2-bit predictor state diagram. So let's see how that fares with the what we were looking at before with the simulations. So here's the first simulation, which gave us 80% accuracy with a 1-bit predictor. So in this case, we start predicting that the branch is taken. So this demonstrates that if you start with a wrong assumption, this can lower this can lower your accuracy. But that's a little bit of an unfair comparison before with the 1-bit predictor simulation of before, because before we were right in our branch outcome. If we had been right here, then our accuracy would have been 90%. And let's look at the second one that had that was a more complex set of outcomes. So here we're incorrect. So it does improve our accuracy from 40% to 50%. So that's a 25% increase, the way that we would look at that. But it does show that your accuracy does increase with a 2-bit predictor in the case that you have more heterogeneous outcomes in the actual outcomes of the branch being taken versus non-taken. So going back to what I introduced at the beginning, that even with the predictor, you still need to calculate the target address. And that causes a cycle, even in the case of the simple pipeline that we are seeing for the ARM version that we're looking at. So again, one way to mitigate that is to only calculate the branch target once and keep around the recently used branch target addresses in a branch target buffer. So in essentially caching the target addresses, and this buffer is indexed by the PC when that branch instruction is fetched. So the buffer and the branch target address is linked to the address, to the code address that has that branch instruction. So if we are fetching a branch, we add that program counter address, then that will be indexing the branch target buffer, and we already have the branch target address. And in the case that we predict that the branch is taken, we can just use that value immediately. So this gives you an idea of how to mitigate the stalling and the flushing of the pipeline, and how to deal with control hazards, which is really the subject of branch prediction. And so far, we have looked at how to deal with hazards in general for pipelines, for structural hazards, data hazards, and control hazards. What we have not talked about are the effect that hazards have in the flow control when we deal with exceptions and interrupts. So these unexpected events that require the vectoring to a service routine is really the hardest of all, although they are part of the control type of hazard, but it's not really a branch type of hazard. It is an exception or an interrupt hazard. The difference between exceptions and interrupts are that exceptions, they come about within the CPU. So some unexpected event happened in the CPU. It could be that there was an undefined opcode because of noise. You can have alpha particles that can change a bit in memories. So if there is an undefined opcode, or there was an overflow from an arithmetic instruction, or the operating system requires a system call, these are things that happen inside the CPU. We call those exceptions. Interrupts, on the other hand, are generated by external entities to the CPU, such as peripherals. And they interrupt the CPU to let the CPU know that this peripheral, this entity that is external to the processor, requires the attention of the CPU. For example, all external I/O controllers will behave in this manner, from your mouse, your keyboard, your disk drive, your communication type of peripherals. So the processor has to go and service this entity, service this peripheral via an interrupt service routine. So given the fact that these types of calls are asynchronous to the operation of the program that is being executed in the processor, it is really hard dealing with them without sacrificing the performance. So this is one part that a lot of work has been done on how to minimize the impact of servicing exceptions and interrupts in pipeline processors, essentially the ones that have a high number of stages and have a super scalar organization with multiple pipelines running at the same time. So what would we do to handle exceptions? Well, for handling exceptions, the ISA that we are studying for ARM has defined the following steps. We have to save the program counter of the instruction that caused the exception. And we're going to save that in the exception link register, which is a special register defined in the ISA. And then we're going to save the indication of the problem in what is called an exception syndrome register. So this is the cause of the exception. And let's say that we assume for the purpose of the discussion that we have a 1-bit, that this is a 1-bit register, and our exception is going to be whether we have an undefined opcode or an overflow. So 0 is going to be undefined opcode, 1 is going to be for overflow. Those are the two exceptions that we are discussing at this moment. Another mechanism is to have what is called vectored interrupts, which there is a handler that is predefined. This is actual software that is predefined that determines or handles the interrupt, and this handler is determined by the cause. So an exception vector register or vector address has to be added to this vector table from some base register. So if we have a base register that has the addresses of all these exception handlers, you could have a vector table that is an offset from the base where the code to handle the exceptions start. So at 0, which would be no displacement from the base register, there we have the code to handle an unknown type of exception. And here on this one, that's where the code would start to handle overflow and so forth. Okay? So the instruction can deal with the interrupt or jump to another handler. So from here, you can just have some small code that handles the exception, or from here you can jump to a larger software handler for the exception or interrupt. So what are the actions that normally these handlers would do? So obviously read the cause and transfer to the relevant handler if you require something more complex. And in there, you would determine the action that is required. If the cause is deemed to be restorable, meaning that you can absorb that error and gracefully continue with the operation of the problem or the program, you would take that small corrective action and use the exception link register to return to the program at the offending instruction and restart the program. If the cause is deemed that is the program is not restartable because it's a catastrophic failure, then you would terminate the program and report that error using the exception link register and the cause register. So that's what the ISA for the ARM has specified to handle these events. But the issues that would be a catalyst for termination of a program are the things that you would see in Windows when you get like a blue screen or something like that. So these exceptions, as I mentioned, are another form of control hazard. Okay, so let's say we consider an overflow on an addition instruction in the execution stage, where you are adding the contents of registers 2 and 1 and putting the result in register 1. One thing that we could do if we detect an overflow is preventing register 1 from being overridden. Why? Because we have an overflow. It's not a valid result. So we don't want to do away with our previous value, which was a valid value. We may complete any instructions that came before this addition that caused the problem, and then at that point flush the addition and all the subsequent instructions, because we don't know if those instructions were relying on the new value of x1. And as we mentioned, as part of the mechanism, we would set the ESR and ELR register values and transfer control to the handler. Okay. The good news is that a lot of the same hardware that can be used or was used to handle branches can be reused, because this phenomenon behaves much in the same way as a mispredicted branch, in terms of having to flush the pipeline, finishing the previous instructions and things like that. So now let's take a look at our diagram with some hardware added to handle exceptions. Here we have the address of a vector for handling exceptions. Where we added that in front of the mux of the program counter, so we can decide, so the controller can decide whether we are going to take the next instruction. We had that before. The branch instruction, so this is for handling branches, or the exception master vector handler. But we still have all the same hardware in place. But we still had the same previous hardware in place for flushing the pipeline and things like that. So again, remember that we can have restartable exceptions, which is we just flush the pipeline, execute whatever the handler needs to do, and then restart the instruction. And that we save the PC in the exception link register, which is what identifies the causing instruction. And also the PC that we have, the next PC, which is PC plus 4, is also saved, and the handler must adjust that if it's going to restart the instruction. So that's a small point to take there. So let's look at the same instruction that we were pointing at here. It causes an overflow. We prevent register 1 from being written. We finish executing the previous instructions, but then we jump to where the handler is. So we force this value onto the PC and we start fetching from here. and you can see how the first instruction here is, or the first couple of instructions are stores. So we are storing important registers that we need for the handling of the exception. So let's look at that sequence in our pipeline diagram here. The first instruction was a subtract, so that is being fetched. It moves to the next stage, and we fetch the second instruction, the AND. Now we fetch the OR, and now we fetch the ADD. When the ADD gets to the execute stage over here, that's where the overflow is going to be detected, and where we have the ESR and the ELR, and the values that go there are just going to be sent down the pipeline through the pipeline registers. So now we're going to get an overflow at this point. We have to flush the pipeline, but let all the instructions that were before, which finish with the OR instruction, execute. We flush the pipeline and install, in this case, 3 cycles, transfer control through here to the handler, and we start executing the instructions at the handler. So when we have multiple exceptions, this issue becomes even more complex. Okay, if the like in the case of superscalar that we're going to see next time we meet, but if you can visualize multiple pipelines in parallel and exceptions that are generated that overlap multiple instructions, they could generate multiple exceptions at once. Okay, so a simple approach is to deal with the exception from the earliest instruction and then flush everything else. We call that approach and phenomenon precise exceptions. However, as we'll see next time, in complex pipelines where you have a superscalar organization with parallel pipelines, to keep these pipelines busy at all times, you need to start issuing instructions out of order from how the compiler placed them in the instruction stream. As long as there are no dependencies, you can do that, and we'll discuss hardware to do that and keep the pipelines busy. So now you have out of order execution and out of order completion, multiple instructions issued per cycle to keep the multiple pipelines busy. So it really can become difficult maintaining that preciseness in exceptions. So that is a big problem that is really beyond the scope of the course, but we did want to raise it so you know that it exists and is a real issue. Okay.